So I always start my talks with an explanation of molecular dynamic simulation. I think for this audience, this is definitely superfluous, but it'll at least give you a feel for how I think about this and how I explain it to other people. So there's really two different things that are both referred to as molecular dynamic simulation. The first of those is the good one on the left, which is quantum molecular dynamics, ab initio molecular dynamics, where we have a collection of atoms or ions and we do a very expensive quantum mechanics calculation to figure out the distribution of electrons between those ions. And then from that, we can infer the total energy of the system and also gradients of the energy with respect to ion positions. And those are, of course, the forces that we can then use to advance one time step in a time integration scheme, get new positions and repeat that many times. And we can learn really interesting things by doing quantum molecular dynamics. It's very accurate, but it is very expensive, and the scaling is oftentimes order n cubed. You can shave that a little bit, but really it limits the size of the systems you can do to, say, less than 1,000 atoms. So that creates a problem where you've got this huge gap between the information that you're getting from quantum methods and what the length scales on which you would actually like to answer interesting questions about, say, the behavior of materials. We can fill that gap by using what we call classical molecular dynamics simulation. Now we simply throw away the electrons, life is good, everything becomes cheap and linear scaling and highly parallelizable on large parallel computers. So we can now do gigantic systems. For example, this shows a shock wave moving through an energetic material where there's a lot of different chemical reactions occurring and energy is being deposited locally due to a void that was in the material that's now closed in this image. So this is on the order of 20 million atoms running the React-FF potential. The problem, of course, with this is that there are issues with the accuracy of the classical potentials that affect all of the predictions that are coming out of these calculations. And so really, machine learning potentials that I'm going to talk about more later are trying and to a large extent succeeding in giving us the best of both worlds. The accuracy of the quantum methods, the great linear scaling and large length scales, and in some cases time scales that we can get from classical methods. There's a little cartoon down at the bottom that shows how all this works together. You've got an MD engine, which more and more is LAMMPS. And from a very small amount of input information, you can get gigantic trajectories, millions and millions of time steps for millions and millions of atoms, both atomic positions, velocities and forces that can give you things like the stress tensor and other interesting diagnostic properties as well. And it's really the analysis of this gigantic mound of data that's the output of the MD code where a lot of the cleverness comes in actually learning useful science. Okay, so I am a member of the LAMMPS development team. I've worked on it for 25 years. And it has grown immensely in its capabilities during that time. It started out as sort of a research project at Sandia, and now it is a worldwide community of developers and users doing all kinds of stuff. The reason why I think it's survived so long and has become so widely used is kind of summarized on this slide. That is a little bit too much to go through. But a key thing is the spatial decomposition message passing parallelism that was in LAMMPS right from the start. And at the time, that seemed like a rather exotic kind of thing to be doing, but it has become incredibly mainstream now as everybody has access to multi-core machines, multi-node machines, and of course now more and more commonly GPUs, which is not actually MPI parallelism. It's really low-level parallelism that you're getting on a single processor. And we've been able to leverage heavily the Kokkos library for performance portability over, say, the last 10 years. And that's given us great performance boosts, but also kept the code base manageable. So we essentially have 2 codes, which is actually pretty good compared to like 100 codes that some projects might have. And those 2 codes are the plain vanilla CPU version and the Kokkos version. And those share, of course, a lot of common code, but at the low level for performance critical components, we basically have to fork. But we've only had to do that fork once, and so even though we're now getting like not just NVIDIA GPUs, but also AMD and Intel GPUs, we're still using the same LAMMPS code base to handle those different platforms. The Kokkos back end gets completely rewritten to handle those things. Okay, so we just recently wrote our first LAMMPS paper in 25 years since Steve wrote his original paper. And for the cover of that, we were asked to provide some artwork for the cover of the issue. And so shown on the right here are 4 representative images that we used for that. And they give you an idea of the scale. So LAMMPS is not just used for the types of material science applications that a lot of people in the room are interested in, which are kind of indicated by these 2 images here. But you can also do a lot of coarse-grained stuff where instead of treating atoms, you're now treating larger molecular units that might represent molecules or something else. So this is 2 micelle, two spherical micelles merging together, which is kind of like a prototype for a lot of biological processes involving membranes. But at the highest length scale here, each particle is about the size of the UCLA campus. And this is representing sea ice dynamics from winter to summer in the Arctic region. This is a collaboration between Sandia and Los Alamos National Laboratory. And here now the particles are what they call discrete element method particles that have, frictional forces and compressive forces and all kinds of other complicated things that are necessary to capture accurate sea ice dynamics. And all of this stuff is supported within this same basic principle of MPI parallelism, which is really amazing. Okay, so some people think there's like a vast army of software engineers working on LAMMPS constantly, but that's not true. There are 4 people who have, say, been working on it consistently for, say, more than 10 years. The first of those is, of course, Steve Plimpton, who just retired. We gave him a special trophy to make sure that he would stick around. It says Steve Plimpton, benevolent dictator for life. The dictator on a daily basis is Axel Kollmeier, who does a huge amount of work handling pull requests and sort of constantly cleaning up the code, both legacy code and also new submissions, and making sure that everything is getting better and better rather than worse and worse in terms of code quality. Stan Moore, my colleague at Sandia, has done a huge amount of work on Exascale performance, and some of the stuff I'll show later was a sort of a direct product of a lot of his efforts over the last few years within the ECP project. And I have done a wide variety of things and keep my fingers in a lot of different pots, but my real sort of interest is machine learning potentials, and how to make them better and better and faster. There are, of course, hundreds more contributors, both historically and also currently. It's a little bit hard for us to count exactly how many there are in any kind of objective way. But one way you can do it is by looking at what GitHub considers to be the number of active forks of LAMMPS at the moment. And that's a screenshot there shows all of the GitHub handles of people who are listed there. There are some other metrics that give you similar results, like on the order of a couple of 100 people at any given time seem to be doing things that make it back into the main version of LAMMPS. And of course, there's lots of people who are just doing their own thing that they don't ever tell us about at all. And that's great too, because one of the important features of LAMMPS, I think, compared to a lot of highly developed codes, is it is still very accessible. You can actually go in and read it, look at how the Lennard-Jones potential is implemented or whatever. And as a teaching tool, I've heard that's extremely valuable. Okay, so this was the cartoon I showed you earlier, and this is a nice schematic of how MD works. But I've used this many times in talks, and I've given it to other people who have used it. And one of my colleagues at Sandia, Mike Chandros, liked it, but felt that it didn't communicate the right level of fear that people should have when they're using LAMMPS. And so he changed it up a little bit and made it look like this. So it's kind of this gigantic sausage making machine. And with any good sausage product, you have to really worry about the quality of the ingredients, and in particular the interatomic potential. And so a lot of what I'm going to talk about for the rest of the talk is actually how to improve the interatomic potential that we're using in all of these gigantic calculations. So this is, of course, something that I've been interested in quite a long time. I think one of the consistent contributions I made to LAMMPS was taking it away from just the toy models like Leonard Jones and so on, but making it work for more realistic potentials. And when I first started, I thought things like Stillinger-Weber and MEME were pretty impressive potentials, and they do carry a lot of value. That has resulted in them surviving over the years. But of course, they have their limitations as well. And so every year or two, it seemed like there was some new potential that was coming along that seemed to be better than the previous one. Whether or not it was better, for a while we did notice that they were getting a lot more expensive. Okay, and so this was a paper that Steve and I published in 2012, the red dots only, where we plotted the cost of a potential in LAMMPS against the year in which it was published. And this is a logarithmic scale. So you're essentially getting this exponential growth in computational cost, sort of like an inverse Moore's law plot, or you could interpret this as a law of constant pain, because as the computers get faster and faster, your potential gets more and more expensive, you're waiting roughly the same amount of time for your answer. And so for some people, that time might be 24 hours, for other people, it might be 6 months. But this was clearly, I think, a case where people were taking advantage of the bigger computers to get more accuracy, or at least try to get more accuracy. The blue dots are ones that we added more recently, and we kind of had to renormalize things a bit because the computers have shifted a little bit. This is all, by the way, cost on a single CPU core. Okay, so we're keeping things very simple. The good news is that the blue dots, not only are they more accurate, because we know this objectively, because now with machine learning potentials, we're actually doing a lot of testing on these things, but they also seem to have broken the inverse Moore's law behavior, which is a great relief, actually. And so I think this seems to be sort of now a sweet spot of 10 to the minus 4 seconds per atom's time step that we're probably going to stay at on CPUs, because the CPU speeds themselves haven't changed much over, say, the last 10 years. GPUs, of course, GPU performance is a whole different thing. It's very highly variable, and it's changing rapidly, so you can't represent it on a simple plot like that, but maybe there are ways we could think about doing it in this workshop. So what I showed you there was just sort of anecdotal, like this is what people might be using, or this is what's implemented in LAMMPS. But I was curious to know what people are actually using, or what potentials most people who use LAMMPS are using. And so I did an analysis of 5,000 papers that cited LAMMPS, which is roughly 1 year's worth of LAMMPS citations. And then I got all of the citations from the citation lists in those papers. I was able to scrape them out of the ISI database. And then I looked at which of those citations occurred most frequently. And I looked at the 200, and I just eyeballed them. And within that 200 top citations, I could recognize a lot of familiar papers that were describing very particular interatomic potentials, kind of like the papers that were used in this year published metric. And so then from that, I was able to actually identify the 22 most popular LAMMPS potentials and how often they were cited. And so that's what's shown on the y-axis here on the log scale, is fraction of those 5,000 papers that cite a particular LAMMPS potential. And then on the x-axis, it's just ordering by rank. And so the red ellipses clearly show that there are a lot of empirical potentials that are still extremely popular. There's 4, actually, EAM, ReaxFF, Tursoff, and Rebo are collectively occupy like 50% of LAMMPS simulations, on this metric. And so that's interesting.
Single time scale for the sampling of the papers?
It's about 1 year, and it was about ending about 6 months ago. So this is very recent stuff. This is work that was done, say, in the last couple of years, right? It will be interesting to look at the historical trend. It was really painful, actually, to get the 5,000 papers out, so I ran out of energy once I did this once. But I'd like to see the whole time evolution of this. I need to find somebody who would help me with that. But the blue ellipses make me happy, because these are the machine learning potentials. I kind of had to game. I started out with 100, and then SNAP didn't make the list, so I bumped it up to 200. SNAP was able to scrape in there. But it is interesting to look at the top one. So Baylor-Parnell neural network potentials, Galbraith's gap approach, deep pot, and MTP. I think that's the 4, and then SNAP. So these are all familiar to us who kind of work in this machine learning potential field. And they are not, occupying a huge chunk of LAMMPS usage at the moment. But I have a feeling that in a few years, there's going to be kind of a revolution. Literally, there's going to be a revolution where the blue ellipses are going to move up to the top and the red ones are going to sink down. I hope that's true. Time will tell. And by the way, if you have any more questions, feel free to interrupt. I suspect I'm not doing very well on time, so please give me some reminders. I'm going to take a little detour. In the last hour that I had to finalize this talk, I changed things up a little bit. I wanted to put in some stuff on how people can implement machine learning potentials in LAMMPS, because that's, I think, an interesting topic for this workshop. Like if you have a new machine learning potential that you just came up with last night and you want to try it out, or you just want to let your friends have access to it, how do you go about this? So we now have quite a few examples of different groups doing this. This is all the different models in LAMMPS that I consider to be machine learning potentials. And people have done it in different ways. And I can tell by looking at some of these examples, like, for example, Deep Pot, that it was actually quite a bit of work to get their existing monolithic standalone code interfaced into LAMMPS, because LAMMPS does its stuff in a particular way that's very good, for example, for spatial decomposition, parallelism, and neighbor lists. But if you haven't been confronted with it before, it's kind of confusing and a little bit counterintuitive. Like, for example, things like periodic boundary conditions don't show up anywhere in the code. They're kind of hidden away in the communication layer, which is surprising, because a lot of these standalone codes actually have very explicit implementations of periodic boundary conditions, like minimum image convention down inside the force loop, and you have to kind of take that stuff out. But it's a lot of work for all of these people to get their stuff in the LAMMPS. Collectively, this was a lot of person years, and the people in question, I think, are all pretty smart. So it's a question of kind of resource management, like how do we make it easier for people to do this in the future? And so I experimented on myself. I took the SNAP model that I had implemented in LAMMPS, and I thought, okay, how could I sort of decompose this into modular units that each by itself would be fairly simple and straightforward? And that resulted in something called the MLIAP package in LAMMPS, and it basically does a couple of things. It first of all strips away LAMMPS itself and replaces it with a simple class called data that's much more kind of intuitive, doesn't have a lot of the cleverness that I mentioned already for LAMMPS. And then broke the actual potential itself up into two parts. One part is the descriptor, which in the case of SNAP is the bispectrum components. And the other part is the energy model, which in the case of SNAP is linear or quadratic. But now it can be, say, a neural network or the PyTorch library or something else. And so the nice thing about this is it first of all makes implementing stuff easier, but it also allows people now to mix and match different combinations of models and descriptors. So if one person has implemented an interesting model like JAX, and somebody else has implemented an interesting descriptor like ACE, those two can now be just plugged together via this data class in the middle. So that's kind of nice. It gets kind of interesting when you're not just running a model, but you're actually trying to train a model. So this slide, talks about both. So the actual force calculation in this MLIP package is pretty straightforward. You calculate descriptors, you calculate gradients of the energy with respect to the model inputs, and then in the last step, you calculate forces in the descriptor class in LAMMPS, which is this last step is the most computationally expensive. However, when you start doing training and you need to know how does the force loss function depend on a particular choice of say, a neural network parameter, and you want to do gradient descent on that, how do you get those force derivatives with respect to a parameter? So dFi d theta, where theta is some model parameter. That turns out to be a little bit more complicated. It's like a second derivative or a cross derivative of two different things. And there's more than one way you can do it. And I implemented two different ways, and they both have their kind of advantages and disadvantages. One of them works great for SNAP, the other one works terribly for, and that one also works terribly for neural networks. The other one, the second one here, works better for neural networks. But there is a third way, and this was originally communicated to me by Nick Lubbers at Los Alamos, who also, by the way, implemented the PyTorch interface into the MLIP package, which is very important. And this third way has now been properly implemented by Drew Roskopf, who's here at the workshop. And this attempts to communicate how it works, but I'll just say that there are two stages. First of all, getting LAMMPS to calculate all those descriptors and derivatives of those descriptors, which are, as I mentioned, very expensive. But then the second part, which is handled in our FitSnap code, interfaces to some neural network library, like, for example, PyTorch or JAX or anything else that you might like. And the key is to sort of separate out those two steps as much as possible so that LAMMPS does its part first, and then PyTorch does its part second. This works super easy in the case of forces. In the case of the loss function that I mentioned, where you're looking at derivatives of this thing with respect to model parameters, there are some pitfalls that you can hit. And actually, there's a really nice paper by Zingraber and Delago on their implementation of Baylor-Paranello, where they provide a lot of good technical information. But they do mention that the size of the data array that contains the derivatives of the loss function with respect to model parameters, it hits on the order of 100 gigabytes because they have to store this for all of the training data at the same time. And 100 gigabytes is manageable, but it's sort of on the edge. And they, I could tell from the carefully chosen words that they used to describe this, that this was clearly a bottleneck and prevented them from doing certain things that they would like to do. So Drew has taken Nick Lubbers' method using double back propagation, and now has the loss function with respect to model parameters, including the dependence on force, packed it into much smaller arrays that are only the size of a single configuration instead of all of the configurations. So that's a really nice thing. And it allows him to train now forces on a wide variety of different models, mixing and matching different descriptors with different energy models. So this is all now in our FitSnap code that does the training. It's at GitHub at this location. I've sort of implied how this works. I'll just say it really quickly. We have a whole bunch of DFT training data for small configurations of atoms that you can either choose in a sort of a hand-curated expert insight method, or you can do a kind of a shotgun approach, like entropy maximization sampling of a descriptor space, which is something that we've worked on with Danny Perez to considerable success. Either way, you have to get this training data, and that's oftentimes the most expensive part of your operation. After that, it's relatively easy in FitSnap to train a model because we're using typically linear energy models, although in the case of neural networks, you can use steep gradient descent and so on. So you can get a model out pretty quick, but you may also have hyperparameters that are nonlinear, things like how many descriptors should I use, what is the size of one atomic neighborhood that works best for this application, and so on. We use something called Dakota to do a search through that space of nonlinear parameters. And that can take, a couple of weeks to find a good set of hyperparameters that works well. But more and more, this has become very robust, and to the point where you do not have to be friends with the one or two current FitSnap experts in order to make this work, but you can sort of, independently of any communication with the core team, you can just download this from GitHub, generate your own data, and make your own potentials. And we've seen multiple groups now do this quite effectively. So I'll just say that active areas of development for us within FitSNAP are developing neural network models, also experimenting with new types of descriptors that are better than SNAP, including the atomic cluster expansion, which is very promising. And we're also finally starting getting into the game of active learning, and other groups I think are ahead of us in this area, but we are planning to catch up very quickly, I'll say. Okay, so I want to put in a plug for some results that Drew got just over the last month or two, where he took all the work that he had done in the FitSNAP code that now allows him to look at lots of different descriptors and lots of different energy models and try it out on a few different material science applications. The first of these is solid and liquid silicon, that's shown here. He looked at a whole bunch of different models, linear SNAP, quadratic SNAP, and also SNAP descriptors combined with neural network models, and got sort of families of potentials where he varied the relative emphasis on energy versus force accuracy, right? So that's why we've got two axes here, force accuracy on the x-axis and energy accuracy on the y-axis. And so now he didn't just stop there and say, well, I like the one, say, that's at the elbow, because that seems like a good trade-off intuitively. Instead, he went and ran the DFT that generated the trained data, ran it again to get quantities of interest that you might get out of a simulation, like radial distribution function, which is quite expensive. The phonon dispersion curves, which are quite expensive to get from DFT. And also a Boltzmann method for getting thermal conductivity out of a DFT code. And so once he had those baseline property values from DFT, he was able to then look at how all these different machine learning potentials performed on those tests. And that's what's shown in these other three plots here. So this is RDF error, this is phonon frequency error, and this is thermal conductivity error, plotted in each case as a function of the force error that was shown over here. And so what really stands out in this analysis is that there's quite a strong correlation across the board between accuracy on the forces and accuracy on the output property from a simulation, not a correlation with the accuracy on energy. And so this suggests that we have in the past perhaps been overemphasizing the importance of energy accuracy, and it would be beneficial to actually give up quite a bit on energy accuracy and get more force accuracy. It is also interesting, something that we've seen in the past, is that adding in the neural network models definitely gives you a better model, but it gives you a model that's about as good as quadratic SNAP. In a lot of these cases, down in the bottom left corner, you see quadratic SNAP and neural network models sitting very close together. And there's something mysterious about that. This is not the first time we've seen this, but it appears that SNAP by itself, linear SNAP, is not so great, but quadratic seems to do really well. And we have yet to see anything that beats it by a lot. And by the way, the Kosinski group at Harvard have a method called FLAIR that is very similar to quadratic SNAP, but it's more like a quadratic SOAP model that they also show very good results with. Okay, so now I'm probably running lower on time, but I'll just say that Drew has repeated this exercise with several other interesting material science systems. In this case, he looked at phonon frequency and thermal conductivity in gallium nitride crystals and saw, again, this very strong positive correlation between property error and force error. Okay, now I'm going to change gears a lot and talk about performance, particularly in the context of large parallel computers and the upcoming Exascale systems. So when Danny and Steve Plimpton and Art Voder and myself first started working in the Exascale computing project, we started out with a pretty good implementation of SNAP that runs on GPUs. And we had done a fair bit of optimization prior to that. And so then we realized that we had kind of put ourselves in a sticky spot because we were required to get a 50x speed up on that base over the course of the Exascale computing project. And of course, the computer was going to be bigger, but we weren't sure that we were actually going to get good performance on that new, yet to be defined computer. And so we started to get quite nervous about how this was going to turn out. And so thankfully, that forced us to concentrate and put quite a bit of effort into improving the performance of SNAP on GPUs. We had an implementation that we thought was pretty good. In fact, Christian Trott, if anybody out there knows him, who's now the main developer of Kokkos, he had done the original implementation of SNAP for GPUs in Kokkos. And he told me personally that we were not going to be able to make it a whole lot faster. So it turned out he was wrong, which is great. This shows over the course of a couple of years, for a V100 benchmark, we got about a 50x improvement in SNAP performance. But that's just on a single GPU. And of course, we want to run this in parallel, and there's a lot of other details there, and also on different hardware. But this was a really strong indication that we were going to be okay in the final analysis. And I'll have a slide now in a second, I think that shows that's true. One of the happy results of that is because this is just a single V100, we were able to then translate that to performance on the entire Summit machine at Oak Ridge, which also has on each node 6 GPUs. The vertical dashed line here shows the number of nodes for the entire machine, 4,650 nodes. This is what's called strong scaling analysis. So on the y-axis, we're looking at sort of a miles per hour measure of speed, million atom steps per node per second. And for a small system, you start out really fast, and then as you add more and more nodes, your speed drops off, and by the time you get to 100 nodes, you're down to, say, 50% of your maximum speed. But that's for a million atoms, right, which in this analysis is considered small. By the way, Ivan Olejnik, who led this particular effort, because it was a collaboration with him and his group at the University of South Florida, is sitting in the back of the room, and he is going to be speaking more about this, I'm sure, on Friday, right? Good. And I have another slide on the science side of this that is, in some ways, even more interesting. But the point about this is I really like this plot a lot because it shows exactly what you would expect to see if you're doing everything right, which is you get good performance and then it falls off. But if you make the system bigger, the point at which you fall off gets pushed out to sort of a proportionately large number of nodes. And so if you want to run on the full machine, you got to go out to about 100 million atoms before you drop below 50% parallel efficiency. Which, 100 million atoms is a little bit big for most science applications, but there are some examples where it's useful, and I'll show you one in a couple of minutes.
Aidan, sorry,
yes.
Really quick, just quick benchmark compared to the speed slides that you showed right at the start. Mm-hmm. Where would so if you had 10 to the minus 4, 10 to the minus 6 for EAM, what would be like the horizontal line on these plots?
Yeah, good question. I'm not going to be able to do that in my head, but
nor could I. That's why I asked.
I think it's going to probably put you in around about the same place as those blue dots.
1,000, the 1,000 kiloatoms.
No, actually, it's got to be because of the power of GPUs. They have an incredible amount of flops on each unit compared to a CPU. Okay, so another way to answer your question is we've actually done a comparison of one GPU node to one typical GPU node to one typical CPU node, right? And I don't have that slide here, but this is something that Stan Moore did. And it was quite striking because it was the best result I've seen so far. And it kind of indicated that for SNAP, if you have a choice in running on a GPU node versus a CPU node, the GPU is going to be faster by about a factor of 100. So compared to traditional CPU nodes, these new platforms are just way more powerful on a atom step per node second basis.
Yeah, and how more expensive is a SNAP compared to Leonard Johnson?
Yep. So, short answer is, if I compare to EAM, on a single node it's about 1,000 times more expensive. But on 100 nodes, strong scaling, same problem size, the EAM speed hasn't improved at all, but the SNAP speed has improved a lot, and so now the difference is about 5x. So instead of 1,000 times, now it's, or say, instead of 500 times, now it's 5x. So that by having a lot of computer power available, which we do more and more, that gap, that cost differential between the empirical potentials and the machine learning potentials has shrunk a lot. And this is not just true for SNAP. I think this is true for a lot of these machine learning potentials. So the extra parallel computing really helps us get more accuracy. Oh, this was the slide. Yep, thank you. You preempted my slide. So this is just showing the same thing, which is on a single node, EAM copper versus SNAP tungsten, it's slightly less than 1,000 times. But you scale up EAM, this is with 4 million atoms, you really don't get much speed up at all. Scale up SNAP, you get a lot of speed up, and so now at the maximum speed, you're now down to about a 5x difference. Okay. Another way to use a large computer is not to do a single system with more and more nodes, although that can work out pretty good. But you can also try to parallelize time, and this is really the focus of Danny Perez's work, and it's been part of our collaboration within the ECP Exalt project. And of course, I'm sure Danny is going to talk a lot about this tomorrow. But this is a result that he just got. It's basically the completion of our Exalt project. He ran on 7,000 frontier nodes with a system, a prototype system for benchmarking purposes that contains about 100,000 atoms. He was able to actually get to about 3 microseconds per day of simulated time. The potential used here was a little bit beefy, I would say, to get more accuracy. A more parsimonious potential that we typically use, because we really do care about speed a lot, without sacrificing much accuracy, we estimate this would give us about 50 microseconds per day, using a combination of all the performance optimization I just talked about and the cleverness of Danny's time parallel methods. And there are 2 of them, I'll just say here. First of all, the par splice method, which is a way to do lots of replicas and have them be independent of each other on different nodes, but then splice them together in an intelligent way so that long time dynamics are correctly recovered. And then the second thing is to do sublattice decomposition within a single replica so that different GPUs are actually running patches of the material, different patches of the material at the same time. And they're talking to each other, but only very infrequently. And that two levels of parallelism is really the key to getting this kind of performance on very large computing resources. Okay, so now I want to talk a little bit about Ivan's work that he's going to talk about more on Friday, which was how do you use a very large computer and the accuracy of SNAP to look at a science problem that people have not been able to tackle until now. There have been some efforts to look at the shock response of carbon in the past using things like Rebo and Tursoff. But all of them have basically shown that when you shock compress these representations of carbon from diamond, you get things that are obviously wrong, and you don't really want to trust anything else from that simulation. And so the goal for Ivan and his group was to see if they could take our FitSnap software, generate their own training data over a huge range of densities. This is about a 3x variation in density, using a lot of different carbon structures, evaluate them all in DFT, and train a SNAP potential. They were able to do this. They not only got high accuracy on training, but they also showed that when you compare DFT melting curves for not just diamond, but also BC8 and simple cubic, the SNAP model agreed with the DFT for the melt curves, to within 10%. And as a bonus, also shown here is the principal Hugonio for shock compression of diamond passing up to the melt curve, along the melt curve, and then up into the liquid. And again, very good agreement with DFT. And so then, with that level of confidence and a 24-hour allocation of time on the Summit machine, we were able to do a couple of really gigantic simulations. In this case, 2.6 million carbon atoms as a shock wave moving through it. The elastic shock wave is shown out here in front. Far behind is heavily plastically deformed carbon, but still in the diamond crystal phase. And then in between is this really complex interplay between shear stress and plastic deformation, which produces sound waves emanating forward from crack tips. And then those sound waves are constructively reinforcing each other and nucleating new crack waves. This is on the length scale here is on the order of microns, and this type of detail would not be seen if we had run the same simulation setup on much smaller systems, because the periodic boundaries, the finite sample size, would have suppressed a lot of this microstructure. So, really great stuff. Similarly, at Sandia, we've developed a SNAP potential for aluminum, supercritical aluminum coming down into the vapor-liquid coexistence region. So initially, this very hot molten fluid that then cools upon expansion into separate vapor and liquid components. And this is an interesting science application for Sandia, I'll just say that. And so what we're looking at here is the initial highly compressed molten aluminum on the left. There's a free expansion occurring towards the right, and a rarefaction wave is moving backwards towards the left. And in between, there is this spinodal decomposition with a very complex microstructure evolution that's occurring, again, on a length scale of microns. In this case, 1.5 billion atoms. And the great thing about both of these simulations is we're getting that information that we have reason to believe is fairly accurate. It doesn't have to be perfect, but it's definitely getting us in the right ballpark of reality. And at the same time is information that we could not get from any other source, whether it's experimental measurements, DFT, which of course can't reach these scales, or continuum methods, which can give you something that looks like this, but only if you sort of build it into your constitutive models and you're sort of, you kind of get in exactly, you get out exactly what you put in, whereas in this case, the behavior is emerging directly from the low-level interactions.
What are the timescales on these simulations?
Yeah, so that's a good point. And
are they reasonable velocities? Are they?
Yeah, they're reasonable for shock events and for free expansion events, but they are sub-nanosecond, which is very short by most most classical MD standards, and very much in contrast to the power supply stuff that I just showed, where we were getting out to microseconds. And so, of course, we want it all. We want the length scales and the time scales and the accuracy. There's still some combinations of those that we can't get. But the exascale computing and some of these other developments have given us a much wider range of access. And so it's really opening up a lot of areas of science that were not accessible in the past.
Aidan?
Yep.
So this free expansion, did you do anything special about load balancing?
Yeah, load balancing is an interesting one. There are things in LAMMPS that give you load balancing, and they always come with a certain amount of overhead. So we try to avoid using them as much as possible. I honestly don't know in either of these simulations if any kind of active load balancing was used. Ivan, do you know in the case of the carbon simulations, if anything special was
used? In load balancing.
Did you do it like once at the start or all the way through?
We do this for some frequency.
Yeah, that's right. So it can definitely help.
Your output takes a lot of time, then you rebalance.
So the thing about load balancing is it oftentimes isn't that important. Like it'll give you a little bit, but it won't be a game changer. And the reason is you don't care about the empty regions. Like if a node has no work, that's fine, as long as there's not very many nodes that have no work. What you really care about are the dense regions, because that's the most expensive region will determine the overall throughput, right? And so as long as, if you have a large number of dense regions, you're probably not going to benefit that much from load balancing. In the case of the carbon, like, if I can pause it. So right now, actually, this is when you really want the load balancing, because now, if you do uniform distribution, only a small number of processors will be working on this very expensive region. And then a lot of the processors will be working on the cheap, low pressure, low density carbon. And so there will be a big benefit at the start. As the whole thing fills up with high density carbon, the effect of load balancing will be less. So it's definitely something to think about for sure. But it might give you like a factor of 2 or something in a lot of cases if you're lucky, because there is a cost associated with that as well. Okay, so how am I doing on time?
10 minutes.
10 minutes, perfect. I've got time just to mention a couple of other things, because I did mention in my talk that I would talk about new physics models, machine learning potentials, and Exascale. The new physics models is really interesting. It's the area that I personally know the least about, but it's really great that I've started being able to form collaborations with a very eclectic mix of people. And some of them are shown here in summary. So first of all, a collaboration between James Goff and Anders Nicolason at Los Alamos has resulted in this really nice new model for uranium dioxide, where the charges on the oxygen and uranium atoms are not just variable, but the model that's used to do that, a charge equilibration model, has a parameter, the electronegativity, that itself is environmentally variable. And this gives much better representation of the DFT data on which this model is based. And thanks to Anders' work on extended Lagrangian Born-Oppenheimer MD, the energy conservation and the accuracy of the charges is also extremely good, and probably better than anything that people have done in the past. A second item is application to magnetic materials, where the spin degrees of freedom are added in as extra variables in the dynamics with our own time evolution. This is work that was started with Julien Tranchede, who's now at CEA in France. And it allows us to build models, for example, that get the correct Curie temperature for iron. And can also combine both structural and magnetic phase transitions in solids. And then finally, there's work with Attila Kanki, Norman Bodine, and Siva Rajamanikam, where we are using SNAP descriptors not to predict the atomic energy, which is typically what people do, but to predict the local density of states that you get from DFT as a real space grid. So for every grid point in a very fine 3D grid with a spacing of, say, 0.1 angstroms, you get a different vector of energy distributions that corresponds to the local density of states at that grid point. And we get this out of quantum espresso. You could also get it out of VASP as well. And then we use a neural network to simply learn as a function of the SNAP descriptors for the grid point, for the local environment of one grid point, learn how to correctly reproduce that LDOS vector. And this then not just gives you LDOS, but it also gives you DOS, it gives you electron density. And if you propagate this forward using finite temperature cone sham DFT, you can also get from the LDOS the total energy. And eventually, someday, maybe this summer, we'll actually get forces with respect to that total energy as well. Shown right here is what happens when you, in a very large system, we of course train on very small systems, but in a very large system, 131,000 beryllium atoms, HCP, we took 3 planes of atoms and shifted them one lattice spacing, so we created a stacking fault. And the color map shows how much the local electron density changes from the pristine crystal to the stacking fault. And there's a lot of interesting structure in this information. A lot of it corresponds to our chemical and physical intuition. We don't have a way to directly test this result, but it shows that we can train on small scales and then infer on very large scales. We have done some testing up to 2,000 atoms where we trained on 256 atoms and then tested on 2,000 atoms, referring back to DFT, and we found that the error at 256 was roughly the same as the error at 2,000 atoms. Okay, that is a slide on the LDOS. That's a slide on the variable charge method. And now, finally, I've made it to my summary. So, a couple of points. First of all, LAMMPS, FitSnap, and many other groups out there in the world who have their own machine learning potential training methods are driving a revolution in atomistic simulation where we can now get the best of both worlds, the accuracy of the quantum methods and the scale of the classical MD. The challenge for all of us now is to make this kind of more widely accessible. So like anybody in the world can now download LAMMPS and run an EAM model without really knowing anything much about anything. It's just incredibly straightforward and foolproof. That's not true yet for these machine learning potentials, but that's where we want to get to. Maybe in 5 years or in 10 years we'll be there. So we want automated large-scale quantum accuracy simulations. So that's, say, an experimental group who have a particularly interesting material. They can just make their own potential by running VASP and by running FitSnap and then running LAMMPS and get out a lot of interesting results for their application without having to talk to any experts. The things that are preventing us from getting there today are, first of all, robustness. So even a small number of bad force predictions in a large MD simulation will destroy the whole thing. And we've had lots of cases of that in our group at different points. And you learn to kind of work around those things, but it requires a lot of cleverness, and we'd like to make that much more automated. One way to get there is by having on-the-fly accuracy estimates. Other groups have done this quite well now, particularly the Kosinski group at Harvard. We are working to build that into our workflow right now. We have a prototype, and the benefit of that is then you can then incorporate it into active learning so that your model gets better and better as you run more and more simulations on your application of interest. And of course, there are lots of physics that go beyond just atomic energies that we would like to get into these models, and that's an area of active research. And so with that, I'm just going to put up a slide with all of the people who have contributed to this talk today, and I'll take any questions you may have.